No, no. Open Zoom. No, you have it here.
Hello, Professor Prem. Yeah.
Hi, Rohit.
Hello. Hi, Ramu. Yeah. Can you hear me?
Yeah, I can hear you.
How do we go?
We asked him to mute. Can you mute for a while? Only when that speaker uses. Oh, yeah. At the time we can just. Yeah. You can hear using your. Yeah. What? Sorry, what? I mean, everything is fine. I mean, such. Okay, you just open it. Sign in. We have five presentations of the first one. So, join where is the link? You have it, right? Maybe. Where is the attachments? Yeah. Your attachments, right? Yeah, this one. Click on. Yeah, go to photo. Yeah, this one. Click. Yes. Yeah. Capital
MAG.
capital name. A small g, small g.
Small A.
Small g. Capital S.
Y.
Small y, small y.
Small I.
Small u. Yeah. Shape. It's already shape, yeah. No, it's not. It's from yours.
Yeah. So more. Height. Oh, nice. So
Why this is connected?
because he wants to present from his computer.
Yeah, so maybe like instructing, I mean, giving the instruction, maybe you can use mic so that everyone can hear. Here the judges, voices can hear like how much is the yeah, in the beginning, right? But they don't need to listen, right? I think so. They need to.
They can hear.
They can hear.
They can hear in this one.
Okay. Okay.
Yeah.
No. No. When I announce the timing, will they hear?
Maybe you have to.
Yeah.
That's
Okay.
one. But when you speak, select.
I have this.
Everybody 4 minutes.
List. Okay. Okay. Good afternoon, everybody. So this is the last session for today. We have 5 student presentations, and it's for competition. So just a time check. We have 12 minutes for presentation and 2 minutes for question and answer, so that we can keep at least 1 minute for set up for the next speaker. I will give an indication when you have 1 minute left. Yeah. So we to start with, we have Hasbur Rahman. He will be talking on elastic nature of domain walls for neuromorphic. Yeah.
Good afternoon, everyone. I am Hasibur Rahman, PhD student from SPMS NTU. I will be presenting here one of the proposed domain-based synaptic device that could be implemented for neuromorphic synaptic application. So before starting the presentation, I will like to thank all the co-authors and the funding agencies. As you can see in the slides, artificial intelligence is widely implemented in every sector, like starting from social media, financial to transport, everywhere. But the issue with its wide implementation is the power consumption. So basically the main root behind this power consumption is the current architecture, von Neumann architecture, where the central processing unit is physically separated from this memory unit. So each time computer process any information, data goes back and forth between these two, and it basically is the von Neumann bottleneck, and that basically slows down the speed and it consumes a lot of power. So to get rid of this and to get an energy efficient architecture, researchers try to mimic out the neurobiological activities of human brain. So we need to understand few basics of human brain. Human brain consists of billion and trillion numbers of neuron and synapses. So let's take this image. So here one neuron that takes information from multiple neurons, and when the input exceeds the threshold, it gives electrical pulse, the spike that moves through the axon, and it basically transferred to another neuron through this element named synapse. So basically what neuron acts as a processor, and synapse acts as a bridge, and which also stores the information. And to achieve this, synapse should exhibit some multi-resistant states. To implement this idea, researchers propose these types of circuit where the artificial neurons are connected through this cross-array artificial synapses. Basically, this is a simulation work, and to realize this experimentally is a bit challenging. So, to understand how this domain-based synaptic device works, so we can start from this point, magnetic tunnel junction, where there are two layers, magnetic layers. One is a free layer and fixed layer, and there are two resistance states, distinct resistance states, and that depends on the alignment of this magnetization. Now, on contrary to this, there is domain-all magnetic tunnel junction. There is a separate layer, spin orbit torque layer. So basically, what happens as a writing method, when current is applied through this, so the charge current converts in the spin current, and it goes towards this free layer and imparts torque on the magnetization. So if there is a domain-all inserted, when current is moving through this SOT layer, this domain-all moves in the forward direction, and depending on the position of this domain-all, there are multiple resistance states created. So this is one thing, but the point is domain-all motion is stochastic in nature. So we need to control its motion to achieve that. Different mechanism has been proposed. It's called pinning method. So you can consider this domain-all as a ball moving in a smooth surface, and you are creating a surface energy barrier or energy well to stop this domain-all at a specific position. So in this way, we can achieve these multiple resistance states. So keeping in mind this pinning approach, so we basically did geometrical pinning method and proposed this idea of ladder domain-all devices. So in this schematic, you can see there the segments are basically parallel pipe that are connected through these middle segments that is basically slanted with this normal to this horizontal. So I also want to mention the physics behind this device. So basically, when domain-all moves and it reaches a particular pinning position, so it gets influenced by two torques. One torque due to this spin orbit torque, and another torque is due to the Laplace torque. So at this position, domain-all basically acts as an elastic membrane, just like a soap bubble. So just like the surface tension, this torque applies here, and due to competition of these torques, different kind of domain-all dynamics are observed. So we basically harvest the domain-all dynamics in simulation, micromagnetic simulation, and in experiment as well. So to understand in depth of this pinning behavior, we need to explore this video. So you can see that initially domain-all performs such oscillation, and finally it gets pinned at a particular position at this junction for this certain current density 5 × 10⁻10 ampere per square meter. We just plotted the position of the domain-all as expressed by X and its time variation source. It's a damped harmonic oscillator. So initially some oscillation, and after 100 nanoseconds, it basically a flat line. So you can think of it as a damped harmonic oscillator. So some sort of SOT force that is act as a external stimuli. The Laplace force in the opposite direction, it acts as a restoring force, and there is some sort of damping also there, damping due to the magnetic material nature. So finally, you see this type of observation. Now taking one of the images of this motion, and we just take the radius of curvature of this surface, and that is needed to calculate the Laplace force. And Laplace force is basically an indication of the pinning strength. So in the variation of the Laplace force with theta, you see that Laplace force increases from 0 degree to 30 degree, and finally it again decreases. Now, so we have seen this damped type of oscillation. We have also explored that domain-all dynamics also. So this type of sustained oscillation for a certain current density 1.1 × 10⁻11 ampere per square meter. So you can see also in this plot, this sustained oscillation. And so basically we can tune the materials parameter, magnetic parameters like saturation, magnetization, Ku, anisotropic constant to get this type of sustained oscillation. So basically it's a damp type oscillation, and from that we can tune that there is some continuous transition to sustained oscillation. Now all these features are included in this phase diagram where basically we explored the domainal dynamics from a large vast current density from 10 to the power 10 to 10 to the power 12 ampere per square meter. So where we have observed different types of regimes as indicated by the different colors, 7 colors, different types of pinning, some oscillations, deepening and deepening with the nucleation. Now, so the previous simulation was for the single pinning side. Here we have taken all the 4 segments. This is the initial state where domainol is inserted, and in the forward time scale, it moves in the forward direction as current of current is applied to these devices, and domainol gets pinned at different pinning positions. These positions are numbered by this yellow color, and you can see that this blue color is basically indicate the domainol and in the magnetization in the up direction, and the red color is in the down direction. So at the end of 100 nanosecond, at the final state, you can see that everything is red. So basically the domainol completely sweep the devices. Now same simulation is observed for 30°, but we see the differences. We get number of pinning site increases. So that basically this angle provides. Now taking this information and we just plot it as a function of time, we see this staircase of nature. There are multiple resistance, multiple magnetization state. Basically, that is in electrical signal, multiple resistance states. So for theta equal to 0°, these 6 states are observed, and for 30°, this number of states increased, and for 60°, it again decreases. So it basically due to the larger Laplace force observed for 30° case. That's why the number of states is maximum for this particular case. Now I will be going to show the experimental results. First, this is at the left. This is the schematic of the SCAT, thin film stat. So where basically the high pressure tungsten and low pressure tungsten is the spin orbit torque layer. COP is our magnetic layer, and this is basically taken to get high spin orbit torque at low resistance level. And just in the magneto-optical car effect measurement setup, we just sweep the out of plane magnetic field and we get this type of car signal. So the squareness indicates the sample has perpendicular magnetic anisotropy and coercivity of around 40 oersted. Now, so the sample stack was deposited by DC magnetron sputtering, and from there optical lithography and ion milling technique, we get this type of devices. These are the optical images of the devices. Now we did the same car microscopy setup. We did the same hysteresis loop plot, and we get this perpendicular magnetic anisotropy. The only difference is that the coercivity gets double in compared to the thin film stack. That because of due to the low pinning, low nucleation site present in these devices. Okay. So now we need to probe the domainol dynamics in the MOC setup, car microscopy setup, and we see that for theta equal to 0°, it takes 80 signals, 80 pulses to completely sweep, and for theta equal to 30°, it takes much larger pulses. For 60°, it becomes again the number of pulses required is again small. So it also shows that for theta equal to 30°, maximum pinning strength is observed. And if you see this video, we get that how intermediate magnetization states are observed also in experiment as well. So initially, a domainol moves very fast along this segment and gets pinned at this position, and that basically gives this flat line in the variation of the domainol motion with respect to time. So we get multiple magnetization state. In total 19 state we observe, and that is a nice result in terms of experimental verification. And so this is the summary. So we achieved the synaptic functionality that was required. We get multiple resistance states. We can optimize the Laplace force, the pinning state, and we get some sort of oscillation. So to wrap up, I just want to mention that we have achieved these types of behavior in micrometer range devices, and if we can get these features in nanoscale also, then that could be a great successful realization.
Yeah, thanks very much. Any questions? So, how do you see the picking time is in between?
Okay, Hasibur.
Okay.
Can you hear me?
What do you think is the best way to reduce it to, let's say, 10 nanoseconds?
Hello, yeah, Rohit.
Yeah. So yeah, I have very maybe just general question. Like the Hasibur started his talk. Yeah, Hasibur started his talk.
If you want to go from blue to completely red,
Yeah.
it takes around 20.
Hello, yeah, tell me.
Yes.
And if you
Yeah.
increase the angle, it
So
can-
Hasibur, are you able to hear me also?
what is the best way to?
Hasibur
reduce
cannot
the
speak.
time?
I mean, he's not able to
I mean,
hear.
this.
But can you ask me
time
question? Yeah, so that I
actually
can
also
ask
depends
him
on
so
the
that he can
pinning
answer.
strength. I mean, the pinning time will also increase. That's one of the reasons. So we don't want. I mean, if you see the total time, that includes also the pinning time. So if pinning time is larger, that's good. Why do we want to decrease? I mean, so if you observe for larger angle, it also increase further.
Okay.
Hello, Rohit, can you type
Yeah.
question?
So,
Yeah,
so my question is,
Because we need to
so
move to-
he has started his talk with the power.
The next talk is from Lee
Yeah,
Shah.
please ask question.
Any questions?
Sorry, I'm not able to understand. Like this is finished or like started?
No, you just ask one question. Please.
Okay, because I have.
Yeah, please go
because
ahead.
The question. Yeah. So
Yeah,
the
please
question is like, so did he measure this power consumption with and without this pattern?
Okay, did you measure the power consumption with or without this pattern? That's Rohit's question. No, because there will be overlap of the voice. That's why I have to ask me to use it and convey.
Okay. Can we take it offline later, or you want to have it now?
Yeah, can we take it offline? Sorry.
Sorry?
Yeah, can you please type it?
Okay. I can make. Okay. So
Okay, yes, thank you.
yeah.
Okay.
Yeah, okay.
Yeah, you
Okay.
can start the
Yeah,
second
thank you,
one.
Raymond. So please invite Lee Shengao. He will be talking on synaptic modulation of conductance and magnetism in cobalt PT film. Yeah. Synaptic modulation, cobalt.
To your face. Okay, good afternoon, everyone. Today my topic is synaptic modulation of conductance and magnetism in COPT field. And my supervisor is Renshaw. And today I will focus on the electrochemical field effect transistors. All the devices are COPT based, and the first one will be using the liquid as the electrolyte, while the second one will using the all-solid
Hello.
state.
Actually, I cannot see the screen.
Okay, first
I
we
cannot
will
just-
find out what is a field effect transistor. For this kind of transistor, upon the application of the gate voltage, here the ions in the electrode will form an electric double layer, so they can form a strong electric field and change the resistance or the conductivity of this film. In this way, we can change the conductance of the film. However, when the gate voltage is above the V threshold, that is when the ions are pushed into the film, then the ions can kind of trapped into the film and it can achieve a long-term modulation. And for this one, it will show the synaptic behavior because it shows both the short-term plasticity and the long-term plasticity. And for these kind of transistors, the ions perform as the neurotransmitters, while the films works as the receptors. Okay, normally this question is how can we find the suitable channel materials and the electrolyte? Usually people will find the materials like this, the oxide.
No one is able to see your slides. Just go Zoom. First you close this one.
Oh,
So just
share.
no,
Cannot share.
You should stop sharing.
Sorry. I'm sorry for the mistakes. Okay, start from. Okay, maybe I can start from this slide because this is the beginning, the introduction. Okay, here we have a traditional transistor. For the traditional one, we usually apply a gate voltage, and will be the electric field, and some charges will be trapped in the film, and then the conductance will be varied. In this way, we can form a traditional transistor. However, for a synaptic transistor, we apply the field when the field is above the base threshold, the ions are being trapped in the film. In this way, we can simultaneously achieve the short-term plasticity and the long-term plasticity. And it just mimics the working principle of a synapse. And in this part, the ions working as neurotransmitters and the films work as the receptor. Well, when we apply the gate voltage, it works as the external stimuli. And then the question is, how can we choose the channel materials and the electrolyte? Usually, people will choose the channel materials such as the oxide, the 2D materials, metal, or oxide with some efficient oxygen, for example, the defects. And for the electrolytes, there are lots of things, maybe the iron liquids, the oxide, or some iron gel, or Heck electron. For the central point here is that we want some channel materials that can accept some particles inside. The materials can be porous, or it can be easily being oxidized, or the property of the thin films can be changed. In this way, also the change can be a reversible change, so that we can tune it to some state and being back to the initial state. And here we use a COPT film. The COPT film can be use the anti-liquid as the electrolyte. And we first anti-clockwise sweep the gate voltage at different steps. And here we can find that there is a huge hysteresis loop. It means that ions are being trapped into the channel, and the leakage current is here, which is quite small, less than 1 nanoampere. So it means that this device can trap the ions in the COPT films, and in this way, it can work as the synaptic transistor. It has the potential. Okay. And then to find out the response of these films to different external stimuli, we apply the gate voltage of different amplitudes from 1.2 volt to 2.6 volt. And here we can find that there is a peak here, and then it gradually decays and stabilizes at a certain value. Here we define the peak value as the volatile change of the resistance, while the stabilized area here, the 300 second as a non-volatile change. It means that the volatile change is a short-term plasticity, while the long-term plasticity is the non-volatile change. Besides that, we also noticed that the ions trapped in the films can also tune the coercivity of this film, because the COPT films show a PMA structure. And then by applying a continuously negative gate voltages, we found that the coercivity is gradually increased. So it means that the ions being trapped in the films can simultaneously modulate the conductance and the coercivity, which just brings in another dimension of a synaptic transistor, because usually it only modulates the magnetism or it only modulates the resistance. Okay. And then to stimulate a biological synapse, the paired pulse facilitation is quite important. Here is that by apply two consecutive pulses and then calculate the paired pulse facility index here according to these equations, it will show two indexes, the tau1 and tau2. I think it's hidden something here. The tau1, okay, I will mention it. For the tau1, according to the calculation, it's around 3 seconds, and for the tau2, it's around 700 seconds, which means that it can be divided into two parts. The first part is the short memory, and the long-term part is the long-term memory. And it also responds to the gate voltage of different frequencies. It means that with a higher frequency, we will obtain a higher amplitude gain, which means that it can work as a frequency filter. Okay, and for this device, it can also shows a good repeatability with both the conductance and the coercivities can switch between the two states, the high level and the low level, and it can okay. And the most important is that we want for a synaptic transistor, we want the resistance and both the resistance and the conductive and the coercivities to be reversible. Here we just apply a train of positive gate voltages and then a series train of negative gate voltages to make the conductance to go to the high state and then being back to the lowest state. It means that this device, the conductivity of this device is reversible. And it is the same for the coercivity. By applying the negative gate voltages, it goes to the higher coercivity state, and then we can make it back by applying a series of positive gate voltages and bring the HE loop to the original state. However, for the liquid devices, it is not usually suitable for the integration of the circuits because it is liquid. So therefore, we want to make it all solid state transistor. And here we fabricate another synaptic transistor based on the COPT film. Here we use the tungsten oxide to replace the ionic liquid. In the tungsten oxide, because it has lots of oxygen ions inside, when you apply the gate voltage, the oxygen ions are being pushed into the COPT films, and partial of the oxygens can be trapped into the film. In this way, we can modulate the resistance and the coercivity of this COPT film. And then we measure the transfer curves and the leakage curves of this device. We first try to sweep at different amplitudes here, from 0.2 volt to the amplitude of 0.9 volt. And here we can find that when we apply a gate voltage around 1 volt, the leakage current is nearly -7 ampere. No, it's -9 ampere, and it is at the so this may be the largest voltage we can apply, because when the leakage current is too high, the oxidations won't be pushed into the channel. In other words, but it will form an oxygen filament. In this way, the device is destroyed. And then we try to sweep at different sweeping rate. And here we can find at the lowest sweeping rate, we can get a highest modulation rate. And then we want to make sure that this device has a good repeatability. So we sweep the gate voltage for 10 cycles. And you can see here, nearly all the loops overlap with each other. However, for the insertion of the oxygen ions, there is a limitation. The limitation is that we cannot apply a high voltage because it will destroy our device. Also, we want to make the device to be as thin as possible so that the oxygens can be uniformly doped into the thin films. In this way, it can get the highest modulation rate. However, in this COPD film, after applying 8 cycles of negative gate sweeps, here we can find that the rising rate is gradually slowed down when we sweep for multiple cycles. And it is the same for sweeping the positive gate voltages. Both of them obey the exponential decay, suggesting that the oxygen concentration will finally saturate in the COPD film. And that is the modulation window of our device. And then we try to apply the gate voltage of different parameters. For example, the gate voltage of different amplitudes, the gate voltage of different time, and the of different pulse numbers. And here we also define the peak point as the volatile resistance, here the origin line. And we define the resistance as the 200 second as the non-volatile resistance. And here we can find that compared with the energy liquid, the tungsten oxide working as an electrolyte is not that good at to retain the oxygens into the channel because the liquid is has a higher migration rate. But for this device, we can also get a non-volatile modulation. And for this device, finally, we want to achieve the learning process of a human brain. For the human brain, when we learn something, after some time, we forget some part, and then after relearning, it can strengthen our knowledge, and after relearning, it strengthens again. And here we calculate the retaining rate. We just first calculate the height of this peak and compare the retaining percentage at this point. After first training, around 37% of the resistance is retained, and the next time it rises to 50%, and the third time it rises to 60%. And in this way, it means that after sufficient training, the resistance can be foreverly changed. Okay, and here we can find that the resistance after the modulation is quite stable, meaning that this device has a satisfying retention behavior. And after each training, it means that the first training of oxygen ions are at the surface of the device, and second, it goes deeper, and the third, it goes deeper. However, remember the previous slides, we mentioned that for this device, it has the saturation problem of the oxygen ions. So after each training, it only rises a little bit and it will finally saturate. To solve this problem, we may need a thinner film of COPT. And for this device, it also shows a good repeatability. After apply a train of negative and positive gate voltages, it can be switched to the high state and low state and going back to the initial stage, which has the high reliability. Okay, to summarize, here we achieve a synaptic modulation on both conductance and magnetism using the ionic liquid as the electrolyte. And we also achieve the similar effect by changing the ionic liquid to the tungsten oxide as electrolyte. However, and for the future work, we are going to use the tungsten oxide electrolyte to optimize our modulation percentage and the energy consumption. And for this program, it is being funded by the NRF, and Prof. Prem and Rinshou supervise the experiment. Mr. Anthony, KU soon helps with the sputter growth, and Mr. Miao Baojun helped conduct the partial of the experiment. And that's all. Thank you.
Yeah.
You said that the oxygen migration is limited in the solid
yes.
compared to the liquid phase. How much is the difference?
I have not compared it, but for this one, I think the modulation window is more related to the thickness of the COPT fields. Because when the COPT film is too thick, then only the electric field is not strong enough to push the ions inside. So the thinner, the better. But we will also need to consider the oxidation problems. When the film is too thin, it will quickly degrade in the ambient atmosphere.
Is there any specific reason to choose COPT?
At present, I'm not sure. But for the liquid and the solid electrolyte, the major difference is the migration rate. So they will have different response time to the gate voltage. Yeah, that's a major difference.
Okay, thank you. Any other questions? I have one question. Yeah, thanks for nice presentation, a good demonstration. But I see the resistance change is very small. So do you have any plan to improve?
Yes, we are. I also mentioned that to increase the resistance modulation, I'm going to shrink the size of the COPT film. In this way, the oxygen ions, either the oxygen ions or the ions in the liquid can be uniformly doped in the whole film. In this way, the modulation rate will be increased.
How much is expected?
Yet I'm not sure.
Anyway, thank you. Yeah. Okay, the next presentation is from Jiru. Okay, let's welcome Jiro. He'll be talking on magnetic transport in niobium iron.
Sorry. Okay. Good afternoon, everyone. And this is Yang Zherui from SPMS, and my supervisor is Professor Wang Xiaoyan. And today I'm going to talk about the hysteretic magnetotransport in layered spin glass niobium iron tellurium. And as an outline, I will give it a rough introduction to the topic first, and I will show you how I prepare the sample and how I make it into a device and make the transport measurement. And finally, I will combine the theoretical calculation to illustrate the result of the experiment. So, sorry, it's not working. Oh, okay, nice. Okay, thank you. And to begin with, I'd like to introduce you the different magnetic system, which I think you should be all familiar with it. And as I live here, there are three different magnetic systems, and the two of them should be very familiar for us because it's already is the basic magnetic element in the area, and it's already widely used in our daily lives. But when we talk about this ferromagnetic and magnetism and anti-ferromagnetism, we would say that it shows long-range order, or we can also say that it's periodically frozen. Let me illustrate this point. Suppose you have you know the direction of a single site of the magnetization of a single site in a ferromagnet. For example, it's point on upward. You would expect the you would predict the magnetization of other points, like you would expect them also to point to the upwards. And for anti-ferromagnet, you can also predict the magnetization direction by the single magnetization direction on single sites. However, there exists an exotic magnetic phase which called spin glass, which is stated as the randomly frozen, which means that although there is non-zero on-site magnetization for spin glass, but you cannot predict the magnetization on other sites by this single site. And this is mainly due to the frustration between the anti-ferromagnetic interaction and the ferromagnetic interaction. And as a result, it's just randomly located, just like a glass. And I would also like to introduce 2D magnetism in layered materials. Finding a magnetic films with a thinner thickness is a goal for the magnetic physics area. And recently, with the advent of two-dimensional one-world crystals, which can be exfoliated down to single atomic layer, with the help of this van der Waals crystals, we are given the new possibilities to find this kind of thin magnetic fields. And like what I show here is for the iron, germanium, tellurium, and it still persists the ferromagnetic order down to single layer. And here, I'd like to introduce an interesting material called NFT, or Novian iron tellurium. And the interesting part of NFT is that structurally speaking, NFT is a van der Waals material with layer structure, as shown in left figure. And from the magnetic properties, it's an exotic magnetic system, since it is proved to be spin glass by our magnetic momentum and temperature curve. We measure the magnetic momentum of NFT by cooling the sample under different magnetic field. And as you can see from the figure, there's a divergence between zero field cooling and field cooling. And this fact signifies the existence of spin glass state in NFT. And here is the structure characterization for our NFT sample. And here on the left is the optical image for the exfoliated NFT thin flakes. And as you can see, the triangular boundary of our exfoliated samples just shows that our crystal is of high quality. And also this electron diffraction pattern proves proves that it shows a good single crystal signature. And last, our TM image just clearly shows the layer structure of NFT. And to study the 2D mechanism properties of NFT, we prepare NFT Synflex down to only for few layers. And the procedure are shown in this slide. And it's totally 4 steps. The first step is to use blue tape to press on the bulk crystal of NFT. And then we detach the tape. And now this few layer NFT was attached on the tape surface. And next, we attach the tape to the our target substrate, where we will make our device. And when we detach our tape again, the bottom few layer flake will left on the substrate. And with some evaporation method, we have our electrons, and to have 4 probes, 4 probe measurement on the transport, we have this whole bar pattern on our NFT device. And we first measure the longitudinal resistance and under different temperature. And you can see that there is a strange drop of the resistance along this T1 and T2 region. And this is where and to figure out the what happens in this region, we take measures on the Hall resistance loop, and we take extract the Hall resistance at 0 magnetic field, and we compare these two figures. We can find that in this T1 to T2 region, our longitudinal resistance just drops. However, our Hall resistance increases sharply. And this fact suggests that there is spontaneous magnetization happens in this region. And next, here we just take the anomalous Hall. If we measure the anomalous Hall effect in our few layer NFT, and we compare our results with previous research on the bulk NFT. As you can see, in our AHE measurement, there is a rectangular shape of this hysteresis loop, which suggests that there is a strong chromatic order in our few layer NFT, which is pointing out of the plane and compared to our bulk NFT. So there is a huge difference between the magnetic property between this two samples, with only the difference of the thickness. Okay. Next, I will talk about the magnetoresistance measurement, and we compared with the bulk sample again, and we found that there is a butterfly-like hysteresis MR in our few layer NFT. And we have our theoretical calculation for NFT to illustrate the result of our experiment. And from calculation, we find that there is an intralayer ferromatic interaction versus interlayer antiferromagnetic interaction. And among these 4 different magnetic configurations, 2 of them share almost the same energy, and they are lower compared to other configurations. And we call it FM and AFM1. And they compete for the ground state. And this is the origin of the spin glass behavior of bulk NFT, and it explains why we have FM order in few layer NFT plates. And Finally, we have our angular dependence of magnetotransport. And the observation is that there's no residual ferromagnetic order when in-plane magnetic field applied, and the butterfly pattern disappears with ASE. This means that this butterfly just comes from the scattering of electron by the magnetic domain wall. And by calculating the magnetic anisotropy energy of NFT, we find that the magnetic anisotropy decreased with the increase of layer number. So we expect that there will be a huge perpendicular magnetic anisotropy expected in the single layer NFT. Okay, sorry. Now I'm going to summarize this. Here is a kind of summary for my talk, and it's an ongoing study, and we are preparing for the measurement for single layer NFT and other exotic transport properties. And I like to acknowledge my collaborators and my supervisors for their previous discussion and the collaborations. And that's all for my talk. Thank you.
So the magnetic measurement you have done in Perl, or
Sorry.
the magnetic measurement, the MT.
Yeah. We have the MT measurement for bulk sample, but for the flake down to 7 nanometers, we can only apply the transport measurement for it.
It was done in random direction.
No. We have the bulk for the bulk NFT. We also apply the magnetic field along the perpendicular direction comparing to its plane. This is possible because we can know from the shape of the our NFT sample.
It is done in discrete or which instrument you use for that?
It's done by our collaborators by the I think it's a PBMS measurement.
Yeah, thank you, Jiro.
Thank you.
The next talk is from Shakti.
Yeah. Am I audible?
Yeah, you are audible.
Okay. I'm unable to share the screen because it says that other participant is sharing the screen. So
Ramu, can you please allow him to share the screen?
are the slides visible?
Yeah.
Okay. So good afternoon, everyone. So today I'll be presenting on machine learning and multi-objective Bayesian optimization based design of iron, cobalt, nickel magnetic alloys. So as we know, machine learning is used for various applications, and these are some of the major applications as shown here. In the past few decades, especially 2 decades, we can say that in material science, machine learning has been used quite extensively for the following reasons. One is to reduce the time and the cost for synthesis, testing, and optimizing of new materials. Second is to explore vast composition space and processing conditions. And third, to solve the highly complex problem of multi-property optimization in materials. For this study, we focused mainly on magnetic materials, and you can see some of the applications of magnetic materials as shown. For our study, we focused mainly on rotating electrical machines. And in order to produce new next generation rotating electric machines, we believe that machine learning can guide us to develop new superior magnetic materials. So let's see how it can help us. Firstly, if we see some of the challenges, there is no relevant database available for magnetic materials consisting of multi-property values. Now, in the literature also, when we looked up, we found very few multi-property studies and especially less mechanical property study of the magnetic materials. Further, we found that there is no multi-property optimized magnetic material available, as it can be seen here in the table shown that let's say some of the materials have very good magnetic properties. They exhibit poor to moderate mechanical, and in the similar case, poor to moderate electrical properties also. So to solve this such a highly complex problem, we think machine learning can help us. Now, as I said, we are focused mainly on electrical machine power, electrical machine applications. So the electrical machine power can be represented by this formula shown here. So in order to develop high rotating speed electrical machines, firstly, we require high strength rotor. Then we would require also high thermal utilization. So for that, we would require low core loss. In that case, we would require high electrical resistivity and high and low coercivity to reduce the core loss. Further, we would also require high thermal conductivity of the material. Now, for high magnetic utilization, as shown, we would require high saturation magnetization or energy product of the material. So overall, in order to design high performance magnetic materials, there's a need of multi-property data. Therefore, what I did was to build a database of 1208 data entries of iron, cobalt, nickel based alloys from previous experimental research. Now, we limited the addition of other elements to maximum of 10%, and the distribution of the elements can be shown, can be seen here in the left-hand side image. Now, for the properties, we collected magnetic properties such as MS, HC, and TC, electrical properties such as electrical resistivity, and mechanical properties such as tensile strength, yield strength, elongation, and hardness. Further, we also calculated the cost using the raw material or the elemental cost of the elements present in the database. Now we can, as you can see here, except for MS, all others properties were taken in log 10 scale. This is to reduce the skewness and also to make the range of the properties in the same level. So now, after this clean curated database of iron, cobalt, nickels was prepared, there was a initial a basic data analysis done. So in this, on this right hand side, we can see the Pearson correlation coefficient chart, which was produced from the data. Now, if I have your attention to the highlighted box, we can see that hardness has a very strong linear correlation with tensile strength and yield strength. Therefore, hardness was chosen as the main mechanical property for the study. Now, if we see the image on the left-hand side, we can see that MS and TC were the most widely studied properties, and HV was the least widely studied property. Now, when we try to find out how many compositions have combined of all the properties, we found that only 0.66% or 8 data entries were available in the database. Therefore, in order to design new multi-property optimized alloy, we would need to require the fill the gaps on the database. Now, for that, we developed a unique imputation strategy as shown in this figure, step by step. Now, for each of the step, 12 different ML models were built, and the best model was chosen based on the lowest MA. Now, let me show the results for this. If you can see in this whole chart of the performance of the models for various steps, we can see that the highlighted box indicates the models with the lowest MAE. Now, these models were used to completely fill the database. After filling the database completely using this unique ML-based imputation strategy,
Can't hear you.
Hello.
Hello. Yeah.
Yeah. Oh, I was disconnected. I'm
Yes.
sorry. Yeah. So, where was the presentation stopped? Can I know?
Okay. Yeah. Go to next slide.
Just here.
Okay, just here. Okay. So, so just to recap that a good multi-property ML model was designed with low MA and high R square. Now, moving forward, we used multi-objective Bayesian optimization. Now, what is the need to do this? First, Bayesian optimization requires less number of steps or samples to explore the whole space, which is our composition in this case, and provide a solution effectively. Second, it is also very efficient in order to optimize objective functions, which are very expensive to evaluate. In our case, using the multi-property model, which is the extra trees model, it's very difficult to optimize for such a huge space. Next, it also helps us to find the global maxima or minima with the less risk of getting stuck at the local maxima or minima, which is the most of the cases in majority of the optimization algorithms available. Now, as I said, the input were only compositions. So we chose only composition dependent properties, which are MS, TC, and cost for optimization. Now, in the Bayesian optimization, we use Gaussian process as the surrogate model and expected improvement as acquisition function. Moving on, so as we can see, these are the results of the Bayesian optimization. Now, in the first table, if we see the MSTC and cost value, these are the target values which are set for Bayesian optimization. And the composition shown are the predicted Bayesian optimization results. Now, using this composition, this was fed into the MIMO-ML model, and we predicted the HC electrical resistivity and hardness. So this completes the first table. Now, in the second table, this is the experimental validation of the compositions predicted by the Bayesian optimization. And if I can get your attention to the last two compositions, we can see that the prediction of the Bayesian optimization was very close to the experimental values. Also, the combination of high TC, low cost, and moreover, high hardness was also observed. So overall, this is the average deviation of the predicted property values from the experimental values. So as in this, we can see that the MSTC cost and HV were the most stellar performance predictions by the Bayesian optimization. So finally, I would like to conclude that in this study, we developed a database of 1208 data entries from previous experimental research. In order to fill up the gaps, we developed a unique ML-based imputation strategy. Further, using this complete database, multi-input, multi-output ML model was developed, which showed overall a low MA and high R square for all the properties, but best for MS, TC, and cost. Further, a multi-objective Bayesian optimization was used, wherein six target combinations of MS, TC, and cost were used. And the overall deviation for these three properties were in the range of 10% from the experimental values. Also, the prediction of the HV values deviated only 15% from the experimental values. Finally, we found two promising novel compositions, which is as shown here, and this has a very high performance compared to the commercially used ternary iron copper nickel alloy. Finally, I would like to thank A-Star for funding our research, and also I would like to thank my research group and my supervisor, Prof. Raju. Thank you. I'm not able to hear. Sorry. I'm still not able to hear. I have no clue why. Let me check. Yeah, I can hear. I can hear now.
This is the problem. You just type your question.
Yeah, I can.
It's not a problem. This mic will feedback.
Okay.
Can you just type your question quickly? Okay. So
Yeah.
what is your question?
So I think you can hear me now.
Yeah, you just ask.
So my question is, oh yes, okay.
You say Roger after you finish your question.
Yeah, are there any questions? I'm a little bit confused.
Can you mute your mic, please? You please mute your mic.
I think there is a question in the chat box. You can just read and then answer. How much
So,
savings you estimate in the development of this alloy for an industrial setup?
So,
Vijay.
in terms of time, I would like to say that this would reduce the development time for this alloy by a fold of 3 or 4 times to the commercial step. And then in terms of cost, when compared to this ternary alloy, these two alloys have almost the similar amount of cost. So with that much cost, the performance of the predicted alloys are quite high. So in that sense, in the cost sense, it doesn't affect that much, but the performance wise, it would definitely impact a lot. And when used in rotating electrical machines, it would make the machines more efficient. So that study needs to be performed. Yeah. So how much energy estimate worldwide you predict hypothetically once you develop the best alloy from your ML? So I estimate that it would affect at least 1%, because just by 1% increment in efficiency of electrical motors, it was reported that.
Stop sharing, Buddy.
Sorry.
Stop sharing your screen.
Okay. Yeah. Yeah. So so even 1% increment in
where can I plug in the
energy of the electrical machine. Sorry, should I stop?
No, it's not mine. Not mine as well. Yeah. It's here. And just scroll down. Can I find it? Okay, I think this one.
Okay.
Yeah. Sorry. Share screen. Well. Oh, okay. Full screen. How do I go? Am I sharing my screen?
Yeah.
Okay.
You have 12 minutes.
Okay.
I'll remind it. One.
How? Oh, okay. Hello, everyone. Today I'm going to present about the induction curing of epoxy composites. I'm Tran, a postgraduate under the supervision of Prof. Terry Steele and Prof. Raju at the School of Material Science and Engineering. So let's get started. For the introduction, epoxy curing involves the transformation of epoxy liquid into a solid state by mixing these epoxy hardener resins or the thermal activation of these epoxy hardener blends. Curing methods impose several limitations. So for example, you can see over here, conventional thermal curing requires a lot of energy and can lead to non-uniform temperature profiles between the substrate and the adhesive. UV curing is limited to transparent substrates and has low penetration depth. Electron beam curing, because it has higher energy, can penetrate deeper into the surfaces and give us more uniform curing profile, but the initial capital investment is very high. That's why we're developing this technology that involves the induction curing that, in our group, we would call it magneto curing. It's essentially the curing of adhesive and magnetic nanoparticles composites under an alternating magnetic field. So you can see the illustration right here inside of a coil. In my work, I utilized a cationic polymerization scheme called a frontal polymerization of these epoxy resin and magnetic nanoparticles. This method offers localized heating by the alternating magnetic field. So we're not heating the substrate, we're only heating the adhesive. It also offers contactless activation, on-demand adhesion, and it's also very energy saving compared to other methods. So first, I'll be talking about the frontal polymerization scheme. First, we have nanoparticles dissipating heat under the alternating magnetic field, which decompose the thermal radicals, thermal initiators, to give us a lot of reactive radicals. These radicals react with this iodonium salt species, giving us a lot of cationic species, which attract protons from monomers to form a superacid. This superacid is very reactive, and it keeps reacting with monomers until it forms polymers. And in the process, a byproduct is the heat from the ring opening polymerization reaction. And you can see after we've turned on the AMF and reactions progress, sometimes we'll actually have enough heat for this process to become autocatalytic, because this heat from the ring opening polymerization will continue to decompose the reactive radicals. Okay, so now we will move on to the magnetic nanoparticles. We call them curing nanoparticles. Why? Because we don't want it to operate over a specific curing temperature, in which case is around 30 degrees Celsius. This is the threshold temperature because we don't want any scorching of the organic coating layers or the resin. So that's why, even though higher content of manganese in these nanoparticles increase the saturation magnetization, which give us better heating temperature, we have to include non-magnetic zinc, so that we can decrease the curing temperature to lower than 300 degrees. So when it reaches somewhere between 260, 270, it starts to shut off, because that's the curing temperature, the threshold of application. And we can see that the nanoparticles, they have super paramagnetic behavior, spinel structure by XRD. Okay. Now I'm going to talk a bit about the induction curing part. So first, let's look at the right. We have nanoparticles dispersed in a liquid resin matrix, and they, under an AMF, they dissipate heat by two main mechanisms: the Brown and New relaxation mechanism. The Brown relaxation mechanism involves particle rotation, which induce shear stresses and dissipates heat. While for the new relaxation mechanism, we have reorientation of atomic dipole moments, and it has to actually overcome an energy barrier that's proportional to the magnetic anisotropy constant, and that dissipates energy as well. So these are two competing relaxation mechanism, and overall, the one with the lower time length over here is the dominant mechanism. And we can actually calculate the amount of heat dissipated by this equation. So let's look at the graph on the right. This is typical magneto-curing temperature profile. So as you can see, after around 10 minutes or so, we see a spike in temperature, which signals the exothermic, the simultaneous exothermic reactions that's happening, and curing is happening. But I want to point out something interesting. That is the red profile. So here we don't see a defined peak in the temperature, which means that we're having these exothermic and endothermic processes during curing balancing each other out. And when that happens, we obtain these curing profile. So the adhesive turns from a transparent liquid into a transparent solid over here. And as you can see, these nanoparticles, they are locked into these cured adhesive matrices. Very stable. Yep. Okay. When working with adhesives, sorry. Is it okay? Oh, okay. So when working with adhesives, right? We usually these questions: how long does it take to cure this adhesive? And what is the amount of a certain type of additives that we have to add into the adhesive for obtain optimal curing profile? So we're looking at the optimization of this magneto-curing process. So on the right, I have the plot of this specific absorption rate. Basically, it tells us how well our composite is dissipating heat at different amount of nanoparticles loading. Surprisingly, we don't find any, for this specific system, we don't find any statistical difference between the specific absorption rate for formulations between 1 weight percent, 2.5 weight percent. The maximum obtained was around 8 watts per gram, but this is very interesting results. We also looked at the degree of curing from DSC. So DSC, we're looking at the amount of residual uncured epoxy after intervals of magneto curing. So we have 0, 3, 5, 10, 30 minutes. And so at 0 minute, we have a large exothermic peak around 140 degrees. However, after around 10 minutes, when looking at the green line, the peak almost disappeared, and we can conclude that for this system, the composite adhesive achieve a very high degree of curing only after 10 minutes. Okay, well, okay, it's partially. Okay, so next we're testing the mechanical strength of these adhesives by the Q test and the last year test. From the Q test, we're testing the magneto cured adhesive
with a normal commercial adhesive. And what we find is very interesting. For the normal commercial adhesive, we find a more stable heel strength, which is the black line, but in the wet adhesive failure, meaning all the adhesives stick to one side of the substrate, whereas the other substrate, no adhesive was found. However, when we look at the magneto-cured composite, we saw that both of the failed substrates have the adhesive, which is cohesive failure, and we also obtain higher heel strength, higher maximum heel strength. Over here, in lab shear test, we found that longer exposure to magnetic field leads to higher adhesion, lab shear adhesion strength, probably because of the higher degree of curing. But maybe when we test it at 1 hour, when the degree of cure is already very high, we don't see that difference. Essentially, mirror curing can be used to obtain very high bonding strength on non-conducting heat insulating surfaces. So I've been talking about how we can disperse these nanoparticles in a liquid resin matrix. However, recent works have also found out that so when you look at the scheme on the left, magneto curing can be carried out on thermoplastics. So thermoplastics, they often come in the form of granules or small pellets. So when I mix that with these functionalized nanoparticles, they actually work. So I found out that magneto curing can be carried out on a non-continuum matrix. And from the thermoplastic melt, because at room temperature, thermoplastic will recrystallize and say, I see that thermoplastic can remelt these thermoplastic can be remelted with the addition of nanoparticles. So you can look at it on the right over here. Yep. Yes, between AMF on and AMF off, the temperature profile is almost identical. And what this means is that magneto curing can be used for recycling of thermoplastic. In addition, magneto curing can be used to not only initiate curing processes, it can also activate. It can also accelerate curing processes because it is supplying heat, and with the heat that's supplied, the rate of reaction will increase exponentially. In conclusion, we found out that magneto curing is a promising method to activate adhesive curing. And in the future, I'd like to look at magneto curing of different types of thermoplastics, as well as developing high SAR, which stands for specific absorption rate nanoparticles. I also want to acknowledge my professors, Professor Steele, Professor Roger John, Dr. Richard Jauhari, who helped me with the initial stage of my PhD and the respective research groups at TU. Thank you. Yeah, so there is one question. So does your magnetic field change polymer and epoxy? These are the previous. That's a very long question. Can you break it down a bit? Okay, let's break it down. So
Yeah. So as a function of magnetic field and magnetic. So if you talk magnetic field and magnetic alignment, how mechanical response?
Mechanical performance wise, because I'm adding these nanoparticles at a very low rate, 1 weight%. So the mechanical testing is actually between a magneto cured state and neat adhesive state. So I think it's more of the how the neat and
magnetosphere pieces are activated for the process of polymerization between the different types of initiation that results in the different mechanical properties rather than the addition of particles.
What about magnetic alignment? Will it affect it? Let's say you if you align those particles during the
Well, the closest I got to that is this when you see initially when I'm with the liquid resin is a black liquid, but when I put it inside an AMF coil, these actually align to the magnetic field, and I guess that they become like localized spots that the dissipating heat from the sides into the middle part. So that's what I observed, and yeah. So that's the only alignment that I observed.
Yeah, thank you. There is one more quick question. So in the stress strain curve, the area, okay, the area under the curve of stress strain curve is lower for magnetofluid adhesive compared to standard adhesive. How are you planning to solve it?
What kind of
You can open the chat.
oh, this is actually not the stress strain curve. This is another type of test, the peel test. So we're I don't know why this image is not secure, but okay. So we actually have this kind of geometry. We actually have this kind of geometry, and we just keep peeling these parts off of each other. So we're benchmarking the amount of force that we have to peel with the essentially the distance from 0 to 2. There's no component that is proving that the be required to peel the normal cases higher than here. We're only looking at the
black one shows liquid force strain.
oh no. So after two, it doesn't matter. This part is when you actually see it peeling off, it's actually the strings between these. So it's actually the substrate itself. It's not the adhesive anymore. Yeah. The part that only matters is from from 0 to 2. That's why I did that one. Yeah.
Yeah, thanks. This is the session for today. I think tomorrow session starts at 9:30. That's interesting talks. So please come.